Welcome everybody, welcome back. In this video, we are going to talk about digitizing sound waves, okay, or data representation sound, okay. We will be discussing how do we represent and how do we save sound as digital. So we already know from the physics that sound is a continuous physical vibration that travels through air, okay. So that is just rapid change in pressure in air, okay. So that is just sound. And sound is a wave, and this wave is continuous. It means just at any different time, okay, or at any time here, there is a value of the wave, okay. And we have gotten infinite values there, okay. In the amplitude, you can just take any two points very near each other, okay. Between them, you have infinite other values. So the analog reality, these continuous variation in air pressure creates analog sound because it is continuous. An analog wave has infinite possible values and infinite precisions at any given moment in time. But we know that waves cannot be stored inside computer in this format. It has to be changed to binary. So see here, a computer processor only understands discrete on and off binary state. To store real world wave, we must force the infinite continuous wave into a finite discrete grid, okay. So we have got an infinite continuous wave, we have to change it to finite discrete grid, okay. So let's see how does that work. First of all, see the difference between analog and nature, okay. Analog is continuous and finite. It means just at different times in every millisecond there is just a different value present there, okay. And it is infinite. It means we have just got an infinite number of different sound levels, okay. But digital, that is discrete. It means it is not continuous. We take samples at different times and it is stepped, okay. So it is not infinite. We have gotten some specific number of sound variations in digital, okay. We will be discussing again in detail about that. Then format of analog is physical vibration and voltage changes, but in digital there is binary code, ones and zeros, okay. That is just the format it is. In storage, vinyl grooves or magnetic tapes. Vinyl grooves are just used in the long discs which were used in the past to play one song, okay. Or magnetic tapes, they can just store analog waves, but in digital just simply we can store that in solid state drives or RAM or HDDs, okay. So in the storage of the computer. So that is just the difference between these both. And sound in reality, that is analog with this different characteristics, and we have to change it to digital to be able to store it inside the computer, okay. So how do we do that? The first thing that we study here is sampling, okay. Sampling is simply taking discrete snapshots of continuous time. See, we have gotten one analog input at different times with equal intervals, okay. We will take samples of this sound, okay. See here, for example, at different time stamps, we will just take sample of that sound. And according to that sample, the sample that we have taken, okay, we will change it to one of the different binary codes for different sounds that are available for us, okay. That will just simply be the amplitude. So see, that changes to something like this. At different times, we will be just taking samples and we'll just simply change that to binary codes, okay. So you have to just know one thing, okay. We cannot record an infinite wave in computer. Instead, a microphone translates air pressure into electrical voltage, and the sound card takes rapid, it means continuous, discrete, it means disjointed, disconnected measurements of that voltage at regular intervals, as we can see here, okay. So this is sampling. Sampling is the process of taking measurements of a sound's wave amplitude at regular time intervals, okay. So that is the definition you can write on your papers for sampling. And sampling rate determines the resolution of time. Sample rate, okay, sample rate is simply the number of different, or the number of samples that we take per second. Okay, so sample rate is the number of audio samples captured every single second, and that determines the resolution of time. So for example, if we take a lot of samples per second, the quality of our audio can get better. If we just make it lesser number of samples per second, yeah, our digital audio will be a little bit different than the original analog sound. Okay, so measurement unit measured in hertz. 1 hertz is equal to 1 sample per second. 1 kilohertz is equal to 1000 samples per second. Okay, and real world benchmark, what do we have? A standard audio CD, kind of a moderate quality. Okay, a standard audio CD uses a sample rate of 44.1 kilohertz. That means that computer takes 44,100 individual snapshots every single second. So that is just a moderate quality of sound that is just used in CDs. Okay, we can just have many more samples per second as well. So just think about this. Okay, 44,100 samples of sound per second. That is just quite a lot. Okay, and for human perception, that is that sounds like impossible. Okay. Okay, the other thing that we have is bit depth. Okay, bit depth determines the resolution of amplitude. And what is bit depth? Bit depth simply means the number of bits available to encode or to store each individual sample. 44,100 samples you are taking per second, and each sample is stored, for example, in 16 bits or in 4 bits or in 8 bits. Okay, so that 4 bit or 8 bit or second bit, that is bit depth. Okay, and we know from before that the number of different combinations given to us by n bits is calculated with 2 to the power of n. What does it mean? For example, if we have gotten 4 bit depth for any audio, it means we have gotten 16 possible values, 16 different volume levels, for example. Okay, and if we have gotten 8-bit audio, it means we have gotten 256 possible values or possible different levels of sound. Okay, 16-bit 2 to the power of 16, which is equal to 65,536 possible values. Okay, which is in standard CD quality, which is just kind of a moderate. Okay, not very high, but that is to the power of 16. It means 65,536 possible values there, in which the bit depth is 16 bits. So this can be just an exam question. And changing analog sound to binary is just a combination of sampling and bit depth. Okay, so that is plotting reality on a binary grid. Digitizing sound is simply overlaying an XY grid onto a continuous wave. Higher sample rates add more vertical lines. Okay, higher sample rates. If you just take more sample rates, it will just create more vertical lines here. Okay, it means just we will take more samples per second. Okay, and higher bit depth adds more horizontal lines. It means we have different levels of sound. Okay, the denser the grid, the closer the digital block matches the analog curve. Okay, so if you just add to the sample rate and add to the bit depth, your digital sound will be just kind of similar or nearer to the original analog sound. Okay, so we have gotten, so here see we have gotten 2 different values. This the first one, okay, this one, it has gotten a higher sample rate. Okay, so see the curve is more similar to the analog compared to this yellow one. Okay, in which we just take a lesser sample rate. Clear? So we have gotten that. Increasing sample rate and bit depth makes the digital sound more similar to the original analog sound, but on the other hand, it also increases to the file size. So that is the fidelity trade-off. Okay, in exam you have to just remember this word fidelity. You have to just use it. Okay, fidelity simply it means how accurately a digital copy matches the original analog signal. Okay, so that is what you have to do. Higher fidelity, it means just the digital sound is more similar or nearer to the analog sound. Lower fidelity, it means just, yeah, the quality is just not that good and it is just a little bit different than the original one. Okay, and the iron law of digital audio, increasing the sample rate and bit depth dramatically improves accuracy and fidelity. The digital copy sound identical to the original. So increasing sample rate and bit depth increases the fidelity. And what is the cost? Okay, the cost is expanding the grid resolution. It means the sample rate and bit depth means capturing significantly more binary numbers, which massively increases the resulting file size. So that is just the price you will have to pay for the quality. And let's just talk about calculating audio size. So they will give you the information, and after that you will have to just calculate the file size, how many bits and how many bytes or KB bytes, MB bytes your file will be. Okay, so let's talk about that, what this is. So the first one, okay, you will have to just know the sample rate, how many samples are taken per second, and that is mostly in hertz or kilohertz. Okay, if it is given in kilohertz to you, you have to change it to hertz. After that, you have to know the bit depth, how many bits per sample your sound is just using. Okay, then after the duration, this should be in seconds. Why? Because sample rate is counted in seconds. For example, if they just give you in second, that's just all right, but if they give you the duration in minutes, you have to change that to seconds first. Then after the channels, it means the same audio is recorded on how many different channels. Is it played in one speaker, in two speakers, okay, something like that. So if it is recorded in one channel, so you will have to just count them once. If it is recorded on two channels, then you will have to just count these things two times. Okay, and that is just multiplied by 2, 4 channels, 8 channels, things like that. Then after that, yeah, multiplying this all things together, you will get the file size in bits. Do not forget, duration must always be converted into seconds before multiplying, and sample rate must be changed to hertz if it is given in kilohertz. Clear? So talking more about the channel multiplier, as we just discussed in the previous slide as well. Okay, see, we can have mono and stereo. You should just be familiar with these two words as well, because in exam they will tell you mono or stereo. Okay, mono audio or mono, it means one channel. The exact same audio is sent to all speakers. So in your formula, multiplied by 1. Mono, that's just number of channels 1. Stereo audio, 2 channels. Distinct left and right audio tracks are recorded separately for immersive sound. Because it is literally double the data, you must multiply your formula by 2. Okay, you are just listening music on your headphones. The sound coming from each of the headphone is just different. Okay, so that is stereo. So you will just multiply everything by 2. So always scan the exam question for the words mono or stereo. Missing this will instantly halve your final answer. Just know that. Then now converting bits into bytes. We have just worked on this before. Bits, so 8 bits make 1 byte. So if your data is in bits, divided by 8, you will just get bytes. Okay, 1024 bytes make 1 KB bytes. So simply that will just if you have your data in bytes, divided by 1024, you will get KB bytes. Okay, and for changing KB bytes to MB bytes, again, just you will have to divide by 1024. That is just a set thing. And yeah, if you want to do the reverse, then yeah, instead of this division, you will have to perform multiplication. Maybe bytes to KB bytes multiplied by 1024, KB bytes to bytes multiplied by 1024, bytes to bits multiplied by 8. Okay, so remember that. Now, just some exam applications. There are some questions. Before just seeing this answer in the video, try to pause the video and just write the answer for yourself, or at least think of the answer. Then play the video and see if you are correct. An analog signal is never fully reproducible in a digital format. Explain one reason why this statement is true. Okay, so think about it. Pause the video. Good. Now the answer is, okay, analog sound is a continuous signal with infinite possible values. Digital recording requires taking discrete samples at set intervals. Because data between the sample intervals is not recorded and amplitude is rounded to the nearest discrete bit, a bit depth value, exact reproduction of the original continuous wave is impossible. So that is the answer for this question. You are taking samples from different times. The data between those times are just simply removed. So you cannot create that back. Okay, so that is simple answer for this. The next question, construct an expression to calculate the file size in maybe bytes of a 3-minute stereo audio, 3 minutes stereo audio file if the sample rate is 44.1 kilohertz with a bit depth of 16 bits. Pause the video, try to solve the question, then come back. Good. Let's check if your answer is correct. See, first of all, build up. Sample rate, that is 44.1 kilohertz. Change to hertz multiplied by 1000, so that will be 44,100. Okay. Bit depth, our bit depth is 16. And duration is 3 minutes. 3 minutes multiplied by 60, so that will be just 180 seconds. And channels, it is stereo. It means we have gotten 2 channels. Now we will just put them in the formula. The final expression, that is 44,100 multiplied by 16 multiplied by 180 multiplied by 2. So that will just give us the number of bits. And we have to just kind of calculate it in maybe bytes. So bits divided by 8, that will be bytes. Bytes divided by 1024, that will be KB bytes. And KB bytes divided by 1024, that will be maybe bytes. So in EDXL, this is just it. You can just get your full score from this. But if you are just taking the Cambridge, in that, yeah, you will have to just calculate this and give a final answer. That's it. Wish you all the best. Do not forget to like and subscribe our channel. See you in the next video. Enjoy your life.